Welcome back to this video series in which I discuss the mistakes that students do while practicing simple linear regression. This is the second video of this series, and in this video I will discuss the method of OLS, that is ordinary least squares. So in this video I'm going to talk about the points where students get confused and the mistakes that they generally end up making while working with the method of OLS. For those of you who have not watched the first video of this series, I'm putting the link of the first video in the description of this video. So please watch that video before you watch this one. And before we get started, please note that this video is not endorsed by any university. I am an online econometrics instructor and I'm just going to share my experience in this video. So let's get started. So in my last video, I talked about the structure of the regression equations. We discussed the population equations and the sample equations. So I've written a couple of population equations over here and sample equations over here. So in this video, I'm going to talk about the method of OLS. So as per the method of OLS, we have to choose A and B such that this expression is minimized. Note that A and B that we have over here, these are the estimators. Alpha and beta that we have over here, these are the parameters. Okay. And as per the method of OLS, this is how we try to figure out the formulas for A and B. Now let's talk about the mistakes that students make while working with the method of OLS. So the first thing is the expression that we have for EI. See, we have YI, which tells us the actual Y values. So YI are the actual Y values. Okay. And YI hat, these are fitted, or you can say predicted Y values. So YI hat are fitted or predicted Y values. Okay, over here I have written capital letters, but that doesn't make a difference. So if you want, you can make them small letters. So let me just do that over here. Okay, so I hope you understand this. So YI is your actual Y values. That means these are the values on which you have the data. That means these values are actually a part of your sample. Y hat are your fitted or your predicted Y values. Now the students do understand that this EI that we have over here, this is the difference between these two Y values. Okay, but sometimes they do forget that what is the direction of the difference. So sometimes they do forget that whether we have to do YI minus Y hat, or do we have to do YI hat minus YI? Okay, well, the right thing is this, YI minus YI hat. So EI is actually equal to YI minus YI hat. Okay, so that's the first thing that you need to take care of, that EI is YI minus YI hat. It is not other way around. You can also take a look over here. So if you take a look at this equation, right? So I discussed this equation in my first video. From here, you can see that EI is going to be equal to YI minus YI hat. So that's the first thing that you need to be careful about. The second thing is this expression that we have written over here. Okay, so notice the expression, it is summation of EI square, right? And many of the times I have seen students writing summation of EI whole square instead of writing summation of EI square. Now see, these two things are not the same, these are different. So what is the meaning of summation of EI square? Summation of EI square means that first you are squaring the residuals and then you are summing them. So basically summation of EI square means E1 square plus E2 square plus E3 square, and this is going on till EN square. Okay, so first we are squaring the residuals and then we are summing the residuals. On the other hand, if I talk about summation of EI whole square, then over here we are first summing the residuals and then we are taking the square of that sum. So basically this expression is E1 plus E2 plus E3, and we sum all the way to EN and then we square the sum. Okay, so this is the meaning of this expression. When we are working with the method of OLS, we do not work with summation of EI whole square. So do not write this. We work with summation of EI square, where we are first squaring the errors and then we are summing it. Okay, and we do have some terminologies for this summation of EI square. It is called residual sum of squares. Okay, it is called residual sum of squares, and the abbreviation is RSS, or you can also call it sum of squared residuals. Okay, it's one and the same thing. So you can also call it sum of squared residuals. If you call it sum of squared residuals, then the abbreviation would be SSR. Okay, so over here, be careful with these two things, that whenever you write EI, it has to be YI minus Y hat and not the other way around. And whenever you're working with the method of OLS, we are working with the residual sum of squares. which is this summation of EI square and not summation of EI whole square, right? So let's move further. The next thing that I want to discuss with you is the linkages. So when you work with the method of OLS, we partially differentiate summation of EI square with respect to A, and we put this partial differentiation equal to 0. Then we do some math over here. Okay, then in between we get this equation summation of yi minus a minus bxi equal to 0, and then we keep on solving this, and then in the end we get that a is equal to y bar minus bx bar. Okay, so I'm not going to talk about the maths that we are doing over here, but I have just written the main elements over here. Now, what are the things that you need to note over here and the things that you need to be careful about? First of all, take a look at this equation. Okay, what is the meaning of this equation? Well, the expression that you see over here inside these brackets, this expression is nothing but EI. So this is summation of EI equal to 0. And how do we know that? Well, take a look at this equation over here, right? Don't get confused between these capital letters and small letters that I have written. These are, I meant to write small letters everywhere. Okay, so these are just small letters everywhere. Okay, so if I take a look at this particular equation, from this equation you can see that EI is equal to yi minus a minus bxi, right? And if you take a look at this particular equation, it is summation of yi minus a minus bxi. That means this term that we have inside the bracket, it is nothing but EI. That means this implies that we got summation of EI is equal to 0, which is sum of residuals equal to 0. Okay, now what are the things that you need to note over here? Well, this is not an assumption. Okay, this is not an assumption. This is something that is happening by construction. Okay, so let me explain that to you, what I mean by this part. So this thing that the sum of the residuals has to be equal to 0, I'm not assuming that, right? I was doing the method of OLS, and in between when I was trying to solve for the formula to calculate A, I ended up with this. Okay, so my purpose was to figure out the formula for A, but in between I got this equation. So the method of OLS is constructed in such a manner that when you are trying to figure out the formula to calculate A, you get this in between, right? So I'm not assuming this, right? So this is not an assumption. This is something that happens by construction. Okay, and this is one of the things that I want you to be really careful about, because sometimes students say that sum of the residuals equal to 0 or the mean of the residuals equal to 0 is an assumption. Well, that is not an assumption. The sum of residuals equal to 0 is something that happens by construction, and if the sum of residuals is equal to 0, the mean of residuals obviously is also going to be equal to 0. So these things are equal to 0 by construction. What is an assumption? Assumption is on the population error, because you do not have data related to the population error. So we end up assuming some things related to the population error. Okay, I'm not going to talk about the assumptions in this video, but please understand this point clearly, that if I say that the mean of residuals, that is the sample errors, is equal to 0, that is not an assumption. Assumption is there on the population error and not the sample error. I mean, think of it in this manner, that why would you put assumptions on sample error when you actually have the data on the sample errors? Okay, so be very clear what is an assumption and what is not an assumption. This is not an assumption. The second thing that I want you to notice over here are the linkages. So what I mean by that is, this equation that we have got over here, that is summation of EI equal to 0. You got this equation when you were trying to figure out the formula to calculate A. And why were we trying to figure out the formula to calculate A? Because we have A in the equation over here in the sample equation. And why do we have A in the sample equation over here? Because A is your estimator of alpha. So we have alpha in the population equation, which is a parameter. A is the estimator of alpha, and when we are trying to find the formula to calculate A, in between we end up getting this equation. So what does this imply? This implies that if I remove alpha from this equation, imagine that I do not have alpha in my population equation. That means I do not need to write A over here. And if I do not need to write A over here, will I have to do this exercise? No, right? Because if I do not have an intercept in my model, then what's the point of this exercise? Why do I need to get the formula to calculate A then, right? Then this exercise is not required. Okay, and if we are not going to do this exercise, that means we are not going to get summation of EI equal to 0, because you get summation of EI equal to 0 when you're trying to solve for A. But if you do not have to solve for A because there is no A in your model, then you're not going to get summation of EI equal to 0. Okay, so if someone asks you that is summation of EI equal to 0 always going to happen, well, your answer should be no. Summation of EI equal to 0 is only going to happen when you have an intercept term in the model. If you do not have an intercept term in the model, then this entire exercise is not going to happen. And if this entire exercise is not going to happen, you're not going to get summation of EI equal to 0. Okay, so be careful with this, that summation of EI equal to 0, this is not an assumption, this is something that is happening by construction, and this only happens when you have an intercept term in the model. If I write a model without an intercept term, that is something like this, y equal to beta xi plus epsilon I. So let's say this is the population model. These kind of models are called regression through the origin. So if you have a model that is regression through the origin, there is no guarantee that summation of EI is going to be equal to 0. The sample counterpart of this equation is actually this, yi equal to bxi plus ei. Okay, so there is no alpha, that means there is no A, that means there is no guarantee that summation of EI is going to be equal to 0. It may be equal to 0, it may not be equal to 0. But if you have an intercept term, and if you're working with the method of OLS, summation of EI is going to be equal to 0 by construction, right? Now let's move to the third thing that I want to discuss over here. The third thing is really an optional kind of thing, but for better understanding, you should know that. So when you're trying to do the minimization exercise, you figure out this value of A. So when you're doing math, ideally you should also take the second order derivative, and you should check that the second order derivative should be greater than 0. Okay, because if the second order derivative comes less than 0, that means this A that you're finding over here, this is going to maximize the expression and not minimize. So if you have to make sure that this A that you have calculated over here, it minimizes the residual sum of squares, then you should ideally check for the second order derivative as well, which should turn out to be greater than 0, because that would imply that this has minimized summation of EI square. This is something that you don't have to do because we know that this is going to happen, but I just wanted to convey it to you that ideally if you talk about the entire procedure, then there is also a second order derivative that you have to do to show that this A is actually minimizing summation of EI square and not maximizing. Many professors and many textbooks just skip this step because they know that this is something that's going to happen. So extra thing that you can just keep in mind. Now let's move further. So now I'm going to talk about the linkages that you should note when you're working with B. Okay, so what is the next thing that we do? We partially differentiate summation of EI square with respect to B, right? We put this equal to 0, then there is some math, we do that math, and then we get one equation which is summation of yi minus a minus bxi multiplied by xi is equal to 0. Then we keep solving this further, right? And then we get that b is equal to summation yi minus y bar multiplied by xi divided by summation xi minus x bar whole square. Okay, so this is what we get. Now once again, let's understand the linkages, right? So take a look at this equation that we have over here. So how do we get this equation? We are doing the partial differentiation, and then we have some math, we do that math, we get this equation, then we keep on solving further, and then we end up with this formula. This is also one of the things that many students find confusing. They do not understand the importance of this. First of all, let's try to write this expression in a simple manner. So this thing that you see in the bracket, that is yi minus a minus bxi, this is nothing but ei, right? Because ei is equal to yi minus a minus bxi. So I can write this as summation of ei multiplied by xi equal to 0. Okay, when we were doing partial differentiation exercise with respect to a, we got summation of ei equal to 0, and when we do the partial differentiation exercise with respect to b, we get summation of ei multiplied by xi equal to 0. Now see, these things that you're getting over here, they actually have an intuition. I'm not going to discuss the intuition in this video over here, but if you want to understand the intuitive idea behind this and behind this, that why are these two considered a good thing, then I do have a video on that you can watch to learn this. And I'm going to put the link of that video in the description of this video. So if you want to understand the intuition that why is summation of ei equal to 0 considered a good thing, and why is this summation of ei multiplied by xi equal to 0 considered a good thing, then you should take a look at that video. In this video, I'm going to talk about the math, that what does this imply mathematically. So what do we mean by this summation of ei multiplied by xi equal to 0, and what do we get by this expression, in mathematical terms? So let's understand that part. So from summation of ei multiplied by xi equal to 0, the question is, what is it that we get from here, and what is the importance of this? Now, before I show you some math over here, first of all, understand that once again, this is something that is happening because of the way the OLS method is constructed, right? So this is happening by construction, this is not an assumption. So whatever we are going to get from here, that thing is happening by construction, that is not an assumption. Okay, so let's see what do we get from here. So I'm going to claim over here that this implies that the covariance between E and X is going to be equal to 0, and if covariance is equal to 0, then automatically it implies that the correlation is also going to be equal to 0. So correlation between these two variables is equal to 0. So I'm also going to show it to you that that how do we get from here to here, right? So for example, let's work with the covariance part, because if we are able to show that covariance is equal to 0, then it will automatically imply that the correlation is also equal to 0. So that's what I'm going to show you, that if this happens, then this will imply that the covariance between the residuals and your independent variable x is equal to 0. So how can we show that? Well, the formula that we have for the covariance is summation of ei minus e bar multiplied by xi minus x bar divided by n minus 1. Okay, so this is the formula that we have for sample covariance between two variables, right? Now let's try to evaluate this. So what is the first thing that we notice over here? That we have e bar over here, and e bar is what? E bar is mean of the residuals, and mean of the residuals is what? It is sum of the residuals divided by the sample size, which is, let's say, n. We know that if you have an intercept term in the model, which in generally many of the models you're going to have, then summation of ei is going to be equal to 0. That means e bar is also equal to 0. So this e bar is of no use over here. We can just, let it go. So that means the expression that we get is summation ei multiplied by xi minus x bar divided by n minus 1. Okay. So now let's solve it further. So I'm going to multiply this term with this term and then this term with this term. So this is equal to summation ei multiplied by xi minus ei multiplied by x bar, right, divided by n minus 1. And now I'm going to apply the summation. So this summation will be applied on this term and then this term as well. So this is equal to summation ei multiplied by xi minus summation ei multiplied by x bar divided by n minus 1. Note one thing, please don't get confused by the way I'm writing the x and the y variable. I'm sometimes writing the uppercase letters and I'm sometimes writing the lowercase letters. So my handwriting is not that good. So whenever I write y, you can just think of this as a lowercase y, and whenever I write x, you can just think of it as a lowercase x. Okay, so don't get confused in this uppercase and the lowercase thing that I'm writing over here. Okay, so from here we get this. Now this x bar that you see over here, this is actually a constant. And why is this a constant? Because this OLS exercise that we are doing this for a particular sample. So imagine a particular sample. This is how your sample looks like. You will have some values of x and you will have some values of y. If you're doing this OLS exercise for a given sample, that means the x bar is also going to be a constant. So x bar is going to be the mean of these values of x. Okay, so it is going to be a number. So that means I can take this x bar out, right? I can remove this x bar from here and I can put this x bar over here. Okay, and we know that summation of ei is equal to 0. So that means this is equal to 0. So ultimately we get x bar multiplied by 0. And what is x bar multiplied by 0? X bar multiplied by 0 is actually 0. So this goes away. So that means the covariance between these two is actually equal to what? It is equal to summation of ei multiplied by xi divided by n minus 1. And now this proves my claim, because in the beginning I claimed that if summation of ei xi is equal to 0, which is 0 because this is how the OLS method is constructed, it is giving you this, then this is going to imply that the covariance between these two is going to be 0. Well, that's something that you can see over here, because if I start with the formula that we have for the covariance between these two, I started from here, and then if I simplify it, I get this. And if summation of ei multiplied by xi equal to 0, that means the numerator is going to be equal to 0. That means this is going to be equal to 0. So if summation of ei multiplied by xi is equal to 0, that means the covariance between the residuals and the independent variable is going to be equal to 0. Or if the covariance between these two is equal to 0, the correlation between these two is also going to be equal to 0. So this is the importance of this summation of ei multiplied by xi equal to 0. It gives you that the correlation between your residuals and your independent variable is going to be equal to 0. And once again, this is holding by construction. I'm not assuming it. Okay, this is how the OLS method is constructed. We end up getting this in between, right? So this is how you can understand the importance of summation of ei xi equal to 0. Okay, so let's move further. The next confusing point that many students have are the formulas that we have for b. So once you work with the method of OLS, you start partially differentiating this expression. You put this equal to 0, you solve it, you get summation yi minus a minus bxi multiplied by xi equal to 0, where this is actually ei. So this means that we have summation of ei xi equal to 0, and I just showed you that this implies that the covariance between e and x is going to be 0, or because the covariance is 0, the correlation between e and x is going to be equal to 0. And then when you solve it further, you get that b is equal to summation yi minus y bar xi divided by summation xi minus x bar multiplied by xi, right? Now, in many of the textbooks, you will see that they will end up writing this as summation yi minus y bar multiplied by xi minus x bar divided by summation xi minus x bar whole square. So this is what I'm going to explain you now, that how do we go from here to here. Okay, so first I'm going to focus on the numerator. I'm going to show you different expressions that we have for the numerator, and once we are done with the numerator, we will talk about the denominator. So let's first talk about the numerator. So I'm going to show you different expressions that we have for the numerator. So I'm going to show you that this numerator that you have written over here, that is summation of y minus y bar multiplied by xi, this is actually equal to the summation of y minus y bar multiplied by xi minus x bar. Okay, that means this is equal to this. So I'm just going to show you that. In fact, not only that, I'm also going to show you that this is also equal to summation of xi minus x bar multiplied by yi. Right? So these are the three things that I'm going to show you, and I'm going to divide this into two parts. The first part is this, where I'm going to show you that these two are equal. Okay? And then the second part is going to be where I'm going to show you that this and this are equal. Okay? So let me first show you that summation of yi minus y bar multiplied by xi minus x bar, this is actually equal to summation of yi minus y bar multiplied by xi. Okay, to show you this, I'm going to start with the left hand side, which is this, right? And then we will show that this is actually equal to the right hand side. So on the left hand side, I have one term over here, so I'm just taking this as one term. This is my second term and this is my third term. So if I'm going to multiply, I'll have to multiply this with this and then this and this, right? So let's do the multiplication. So this becomes yi minus y bar multiplied by xi minus yi minus y bar multiplied by x bar, right? And then we have summation over here. Now I can apply the summation over here and over here. So this is equal to summation yi minus y bar multiplied by xi minus summation yi minus y bar multiplied by x bar. Okay, now once again understand that this OLS exercise that we are doing this for a particular sample, and this is how a particular sample looks like. You will have some data on x, you will have some data on y, and this x bar that you see over here, this is the mean of these x values that you see over here. Okay, so basically x bar is going to be a particular number. If x bar is a particular number, I can remove it from here and I can write x bar over here. Okay, now if I write x bar over here, this expression becomes summation of y minus y bar, which is actually equal to 0, because this is one of the properties that we have in statistics. Okay, if you do not recall this property, then just give me few seconds, I will explain that to you. But if this becomes equal to 0, so if summation of yi minus y bar is equal to 0, that means this second term that we have over here, this will go away and we'll be only left with summation of yi minus y bar multiplied by xi, right, which is the right hand side. And that's what I claimed, that these two are one and the same thing. So we started with the left hand side and we are able to prove that this is equal to the right hand side. That means I can easily go from here to here. It's not an issue. Okay, now let me show you that y is summation of yi minus y bar is going to be equal to 0. If you do not remember this, well, this is a property. You can imagine this in two ways. You can take certain values of y. Let's say I take three values of y, 1, 2 and 3. Now what's going to be the mean of these three values of y? So y bar is going to be equal to what? 1 plus 2 plus 3 divided by 3. So this is equal to 6 divided by 3, and that is equal to 2. So y bar is equal to 2. So if I create a column over here which says y bar, then I have 2, 2, 2 over here. And then if I create y minus y bar, then 1 minus 2 will become minus 1, 2 minus 2 will become 0, and 3 minus 2 will become 1. If you sum this, this sum is your summation of yi minus y bar, right? And if you sum this, you will get equal to 0. Okay, and this is not something which is happening only for these values. This is something which is always going to happen. This is a property. If you want to see it mathematically, this is how you can see it, that y bar is equal to summation of yi divided by n, and this implies that summation of yi is equal to ny bar, right? Now over here, what do we have? We have summation of y minus y bar. So how can we write summation of y minus y bar? We can write summation of this minus summation of this. Okay, so this is equal to summation of yi minus summation of y bar. Now y bar is going to be a particular constant, right? Because if you are given a sample, y bar is just going to be a number. So if you sum a number n times, you get n multiplied by that number. Okay, so this is actually equal to summation of yi minus ny bar, and by this definition you know that summation of yi and ny bar are one and the same thing. So they are equal to each other, and they are always equal to each other because this is how y bar is defined, right? So that means summation of yi minus ny bar will be equal to 0, and this is something that always happens. That's why this term over here is 0. Okay, and we end up getting this. So this I showed you. Let me show you some more math over here. So I showed you that we can write summation of yi minus y bar multiplied by xi minus x bar as summation of yi minus y bar multiplied by xi, right? Now I'm going to show you some more things related to these expressions. Now this thing that you have over here you have summation, and then this is a variable and this is a variable. So this is multiplication of two variables. So it doesn't matter which variable you write first, right? Because either way you're going to multiply them and then you're going to sum. So I can also write it as summation of xi minus x bar multiplied by yi minus y bar. It doesn't make a difference. Okay, so and now I'm going to show you that this is equal to summation of xi minus x bar multiplied by yi. So ultimately these four things are equal to each other. Okay, so let's see how can I show that this is equal to this. So once again, I'm going to start with the left hand side. The left hand side is summation of xi minus x bar multiplied by y minus y bar, and for the multiplication I'm going to think of this entire bracket as first term. This is my second term and this is my third term. I'm going to multiply this with this and this with this. So I'm going to get summation xi minus x bar multiplied by yi minus xi minus x bar multiplied by y bar, right? And now apply summation on this term and apply summation on this term. So this is equal to summation xi minus x bar multiplied by yi minus summation xi minus x bar multiplied by y bar. Now once again, y bar is a particular constant because we are doing this OLS exercise for a given sample. So I don't have to write y bar over here. I can actually write y bar over here. And this summation of xi minus x bar is going to be equal to 0 because as I just showed you that sum of deviations from mean is always equal to 0. So by using the same property, this will become y bar multiplied by 0. Okay, so this will go away and this is just equal to summation of xi minus x bar multiplied by yi, and this is what I claimed over here. Okay, so what is it that we have learned over here? We have learned over here that summation of yi minus y bar multiplied by xi minus x bar, okay, this is actually equal to summation of yi minus y bar multiplied by xi, and this is also equal to summation of xi minus x bar multiplied by yi. Now I understand this is a lot of math to keep in mind, so let me tell you a trick. See, if you start with this expression, then in this expression you have yi minus y bar and xi minus x bar. That means both the variables are written in deviation form. So this is in deviation form, y minus y bar. X is also in deviation form, it is xi minus x bar. Now out of these two bars that you see over here, that is x bar and y bar, if you remove any one of them, it won't make a difference. So for example, if you have to go from here to here, basically what's the difference between this expression and this expression? Well, if you just remove x bar, you will go from here to here, right? This is the difference. Similarly, if you have to go from here to here, you just remove y bar from here, you just remove this y bar, and you will have this expression. So what is it that you can do? That if you have y minus y bar multiplied by xi minus x bar, that means both the variables are written in deviation form. You can just write one of them in the deviation form and the other one as it is. It doesn't matter. If you want, you can remove y bar, it won't make a difference. If you want, you can remove x bar, it won't make a difference. Just keep one thing in mind, that do not remove both of them at the same time. So you cannot write this as summation of yi multiplied by xi. This is not equal to these. Okay, so you cannot remove y bar and x bar both at the same time. You can remove only one of them. Which one you move, it won't make a difference. If you want to remove y bar, fine. If you want to remove x bar, fine, but do not remove both of them. Okay, So this is how you can keep this in mind. In fact, there is one more expression that we have for the numerator. I have already shown you 3 different expressions for the numerator that we have in B formula. The other expression that we have for the numerator is summation of xi yi minus n x bar y bar. Okay, this expression is also quite simple to get. Basically this thing that you have over here, this. Okay, you multiply these two brackets and you keep on solving it. Ultimately you will end up with this. So the numerator can also be written as this. If you want to see that how can we get from here to here, well, I have a video in which I have discussed different formulas to calculate B. I will put the link of that video in the description of this video. So if you are interested in taking a look at this formula as well, because at some of the places you will see this formula, then do take a look at that video. That video talks about that how can you get this numerator. Okay, so this is all about the numerator. Now we can also talk about the denominator. So when you first solve the formula, the denominator you get is summation of xi minus x bar multiplied by xi. Okay, so this is the denominator that you get when you first solve for the formula to calculate B, and then you will see at certain places that they will write the denominator as summation of xi minus x bar whole square. So how do we go from here to here? So basically, how do we go from summation of xi minus x bar multiplied by xi to summation of xi minus x bar whole square? So let me show you this as well. This is also quite simple. So summation of xi minus x bar whole square, this can be written as summation of xi minus x bar multiplied by xi minus x bar, and we have to show that this expression is equal to summation of xi minus x bar multiplied by xi, right? So this is the left hand side and this is the right hand side. I'm going to start with the left hand side and then I will show that it is equal to the right hand side. So the left hand side is what? It is summation of xi minus x bar multiplied by xi minus x bar. Think of this as one single element, think of this as your second element, and think of this as your third element, and then multiply first with second and first with third. So LHS will become summation xi minus x bar multiplied by xi minus summation xi minus x bar. So this is xi minus x bar multiplied by x bar. Now once again, you don't have to write x bar over here because it's a constant. You can write it over here. Okay, so you can remove x bar from here. Summation of xi minus x bar will become equal to 0. I have discussed this with you because sum of deviations from mean is equal to 0. So this part is equal to 0. That means the second term is x bar multiplied by 0. So this entire second term goes away. That means we are just left with the first term, which is summation of xi minus x bar multiplied by xi. And this is what I wanted to show you, that summation of xi minus x bar whole square can be written as summation of xi minus x bar multiplied by xi. Right? So this is how you play with formulas. In fact, if I have to tell you, this denominator that you see over here, this can also be written as summation of xi square minus n x bar square. It's quite simple to go from here to here. All you have to do is apply the formula of a minus b whole square and then expand this. If you want to learn how to go from here to here, well, once again, the link of the video is in the description of this video. You can watch that video. Right? So these are different ways of writing the numerator and the denominator that you get while you're working with the formula to calculate B. And this is one of the things which used to confuse many students because they used to see different expressions for this B's formula. So now I have shown you the multiple ways in which you can write the numerator. I have also shown you the multiple ways in which you can write the denominator. So I hope this is going to help you in avoiding all those confusing points. So this was the second video in this series. I hope you liked it. I'm working on uploading many more videos. If there is anything in particular that you find confusing, then please feel free to post a comment on this video and I will take a look at it. I have also created a quiz on simple linear regression. The link of that quiz is in the description of this video. You can attempt that quiz to test your basics and I will see you in the next video.